So let's go into Q&A session. We're a little bit ahead of schedule, but that's totally cool.
Okay.
Obviously, Mr. Mission Control has had his hand up. So, sir, let me ask you to go first.
Hey guys, I'm the inside information guy to Davey Boy from Generation Z there. I've been studying frequencies. I'm an occultist or a metaphysician, and I've been studying frequencies and stuff like this for a long time. And then I come across Dave Winter's information, and been just messing around with some audio and stuff. But real quick, I wanted to let you guys know the main build of the cylinder UAPs. I think that I have the answer to their propulsion. What it is you've got 9 toroidal, pretty much Namibian magnets, or we're coming up with these new materials every day, if you pay attention to the science articles. So like Kagome metals and stuff like that. So
okay, well let me stop you for a second. Do you have a question for Rob? Because that's kind of where we're at.
Oh, I'd like to know if he's familiar with what's going on with the Havana NexRad spiral signature we're getting off the Doppler, off the, like, windy radar satellite, because they're obviously heating the ionosphere and pulling that cold air down for the last month. I've got screenshots, and I also want to know if he's familiar with monitoring CERN's activities via the BLF Cumania Marconi antenna in Italy readouts.
Haven't come across it.
And
okay.
and the effects to the Schumann resonance be with what CERN's doing. And do you know about the quantum gravity experiments they're fixed to pull off or attempt? Maybe do it now.
Okay.
Which they say will inherently change our reality of time. If they didn't already do that in 2012.
Maybe.
I'll yield the floor.
Okay. So yeah, Rob, do you have any thoughts on those, or?
No, I've not come across any of that. No. So
okay. Yeah, and those are things worth looking at. But so let me go to Daniel Whiteson next then.
Hello.
Hey, Daniel.
Thank you
there
very
you
much. So I'm trying to understand the basic mechanism of this propulsion. It seems to me to be equivalent to trying to push a box from the inside. How do you provide an external force using only internal forces?
I think, as far as I understand it, the idea is that you mimic the effect of an external force by manipulating the wave inside. It does sound kind of like pulling yourself up by your bootstraps. I will admit that.
Doesn't that violate conservation of momentum?
Well, I think there is. I haven't studied it in great depth, but he does mention something about that the momentum is cancelled out, because a light beam, when you reflect it from a mirror, you have momentum reversal, and because you're doing it at both ends, it cancels out the momentum. Again, I'm not clear on the details. I'm not. Essentially, I think the problem that I found looking at it is that you're creating a wave that goes, one generator goes one direction, the other goes the other. What happens to the energy of that wave when it hits the other side? Because you're not directly using that wave to bounce back. You're artificially bouncing back another wave. So
but it's all
I think
internal, right?
There may be a question of what happens to that, to the wave that you're producing when it gets to the other side, unless it's somehow being reused and redirected. Now they're feeding energy in. The idea is that you feed energy in all the time from these pump beams to create your full wave mixing.
But if you're inside a spaceship and you throw a tennis ball on the inside wall of the spaceship overall doesn't move, right? I mean, there's a basic principle there. This seems to be ignoring.
Yeah, I mean, this is the thing, is that what he's saying is that you can induce this kind of distortion, this kind of standing wave mixing by applying an external force. And so it does sound, you could call it, I don't know, cargo cult maybe, that it's if you you then reproduce the effect of an external force, that it should then have the same effect as that external force.
But that violates conservation of momentum, so it can't, right?
Yeah, this is where I'm not 100% sure myself about what happens to the energy that you've produced, and when it hits the other side, where does it go? Is it being reused, redirected in some way? So
well, my understanding
yeah,
is that every attempt to produce this in the lab has failed. So I don't understand what the basic idea is.
I think what he's saying here is that if you have like the Sawyer drive, which is just pushing from one side, you have one generator, that it will not, it requires basically some sort of external force, which Sawyer himself has said.
So how is it a propulsion system if it requires a separate external force? That's just an inert object, right?
No, that's what I mean. This one doesn't. This is what Larry Reed is saying. This is the advantage of his system over others, is that you are, instead of just sending a beam in one direction, you're mimicking the effect of an external force. And admittedly, yeah, it does. I'm dubious about it myself. I just thought this needs a wider audience, really. Yeah, so what he's saying is, as an extension of, if you assume this local generation of inertia, the de Broglie matter wave, his description of it, or that there is a macroscopic equivalent, that he's saying that if you characterize that form, that waveform, as applied by an external force, if you were then to reproduce that waveform in the same situation without applying an external force, but by supplying it with energy, and however much energy it requires to do that, that you should, in theory, assuming there is such a thing as the inverse Doppler or effect in this context, because I think there have been some experiments which have shown an inverse Doppler effect, but I'm not sure it's in exactly the same kind of context as this. So I think this is just his idea. It hasn't been tested as far as I'm aware. So, but it's something which doesn't seem to be too difficult to kind of just to see what the effect is, to see what happens if you can actually, if by mimicking the wave that you would produce, whether it would produce.
Well, thank you for the frank answer. I appreciate it.
Yeah. Okay. Thanks.
Awesome. Well, and thank you as well, Daniel. Let me go to Michael Boyd next. Michael?
Hey, I think Jeremy was ahead of me, actually.
Oh, it was, well, no, it shows you ahead of him.
Oh, okay.
I think you beat him to it. Go for it. Go for it.
So I got a question about dimensions. What's the length of the cavity that you're talking about here?
He doesn't really specify length. I'm guessing a few meters would probably be enough.
A few meters?
It doesn't have to be enormous or tiny.
So I've worked with a linear accelerator that's about 18 inches, and the cavities get smaller the closer the basically what you're creating is a standing wave in each of the cavities.
Mm-hmm.
And then as the cavity gets narrower, the speed of the electrons increases to closer to the speed of light. Mm-hmm. Then at the narrowest cavity, there's the one I worked on, there was a piece of tungsten metal, and it created what's called Bremsstrahlung radiation, and it was a 6 million volt X-ray. So, I mean, obviously you can use it to create a whole lot of energy.
Yeah.
What I don't follow is how you create thrust or inertial energy, which in my mind is something different from electromagnetic energy.
Yeah, I think this is the equivalence they're trying to draw here, that you feed in energy from these pump beam transmitters. So there's no requirement that it has to power itself, that you are powering it externally. And I guess the difference between the blue shift and red shifted frequencies gives you the kind of magnitude of the thrust you should expect to see. I think that's what he's driving at there. Because obviously, if you look at an electron has a huge amount of energy in a very small space. And so he's saying essentially you should be able to scale that up. I mean, I'm not sure what levels of power would be needed to move it at, say, the speed of sound, but I guess that could be calculated.
Well, I know, for example, with a proton, you need a cyclotron to spin it up to get enough inertial energy to get to the speeds of light. So the other issue in my mind is the relationship between the mass of the proton and the mass of the electron. The electron is what, 1,640 times lighter than the proton?
Yeah.
So how do you get inertial energy out of that little mass?
Well, I think the idea is that the inertia comes from the fact that you've confined electromagnetic energy into a very small space. That is the reason why it has inertia. That just pushing against it, it resists your push, and that resistance is a direct product of the fact that you trap this wave, and that so it's a direct one. Well, not, I suppose, not one-to-one. It depends on your choice of unit, but there presumably there could be, you could imagine some scale where you have 1 Newton of force. It relates to however many giga electron volts of energy, or I mean that is already mass is effectively measured in electron volts, and so I think it's really just a case of a choice of unit. The central concept is that, and as I say, if you read the original article from Jennison, that he can derive E equals mc squared and F equals ma at the same time from this system. I'll post a link to these articles in the chat later, so you can have a look. But even it's just a classical calculation. There's nothing very complicated about it, which is the amazing thing for me. And I think for people like Mike McCulloch, this is why he was so surprised when he read it, because it's like, this is so, it's applying known physics, classical physics, in such a kind of a simple way that you get something very profound out of it. That it's a kind of it's a very attractive idea. So I think there's no real issue with the local calculation of inertia, in terms of the papers that were produced were peer reviewed, and in fact Jennison himself was very humble about it. He said, well, I'm probably not the first person to realize this, but I'm the first one who wrote it down. So he's saying this is so kind of blindingly obvious that probably every other physicist can think of it, but they've just never, it was so simple they never thought to actually write it down anywhere. So
So thank you for answering my questions. It's appreciated.
okay.
Great
Awesome.
presentation.
And Michael, thank you as well. Let me go to Jeremy Rys next, sir.
Hey, can everyone hear me? So my question comes from Sky's the Limit, and it has to do with the signal generation on the hull of this craft. Like, what methods would you be using to actually generate the frequencies or the signals in the hull? And does the frequency in the / phase shift increment matter? Like, for example, when shifting waveforms, do they need to be like a fraction of a degree? And what maybe different fractions might work, like, quarters, ninths, fifths, Yeah,
I'm not sure of the exact values, but as I was saying earlier, the information that I've used for the presentation is I've trimmed out a lot of the more detailed calculations. So if you search out, or I will put in the chat later, the Larry Reed's own work, he's included all the calculations that he's used to the variations of phase velocity, group velocity, the ways that it's affected by the refractive index. And I assume that the transmitters that are used are just pretty standard microwave transmitters. There doesn't seem to be anything particularly complicated about it, that they're just, they have to be manipulated, very precisely in terms of the frequency shift and phase shift to get the desired effects, but to get nice smooth acceleration, deceleration, and so forth. Yeah, so the exact calculations are all in there in the EM Propulsion Drive presentation by Larry Reed. There's one in his ResearchGate and in academia.edu. In his book, he actually doesn't really cover it in great detail, but in the presentation, there are pages of calculations. So I would advise your viewer to look at those. Well, I would say I'll put things in the chat later that will point you in the right direction.
Awesome. Yes. Thank you for your answer. And sorry, my audience I was muted for them, but you guys could hear me. So
yeah.
All right, awesome. Okay. Well, thank you, Jeremy. Let me go to Jarod next. Jarod.
Hey, Rob. Great presentation. Two questions for you. One, with all of these resonant cavity type propulsion devices, it always seems like the quality factor, the Q factor, comes massively into play. If it's not above like 10 million, you're going to be pumping in way more juice than the amount of propulsion you're going to get out. I didn't really hear you go over any part of that. Second part of the question is, you were referencing like McCulloch's work with it. The dynamic Casimir effect also seems to be a very important component in a lot of this. And I didn't hear you mention any of that. Could you talk a little bit on how that factors into stuff?
Yeah. Right. Let me think. Yeah. So sorry, the first part of your question.
The Q factor.
The Q factor. Yeah. Sorry, the Q factor. Yeah. I think that is specific to the kind of the Scheuer type drive where it's the radius changes, the curve, the sides. Yeah. The width of it changes from one end to the other. And what Larry Reed's, I think he's saying his operates on a different principle, that it's almost like by accident that Scheuer and Canet and people like that, that they have something which sort of works, but works a little bit. And he's saying that actually the Q factor is kind of irrelevant to his idea, because his idea is fundamentally that you're just sending a wave back and forth, and you're just changing the shape of it, and to mimic or potentially, I suppose, create a de Broglie matter wave that moves in a way. So his whole concept is different, although the basic elements are similar. His kind of idea of how the whole thing works, he's saying that, well, this is why it works, and this is why theirs doesn't quite work, or the Q factor is kind of it's not relevant to his work as far as I can tell. Now for the second part, I only really mentioned Mike McCulloch's work because he had looked at this paper as well, the article about the electron. So I'm not sure what bearing it has on his own work. I haven't really looked into the links between that and QI, although I think he has used it as he's given QI as kind of an explanation for why this works. So he considers that as supporting evidence for it, but I haven't really looked into that in detail. So thanks.
Awesome. Let me go to Harold Tavares next, sir.
Oh, hey, thank you for the presentation. And my question has to do with the vector sum of the forces within the cavity. But first, I want to thank you for providing that PowerPoint ahead of time to review on that it was put on APEC website. Now, to my question is, I noticed the inside the cavity, you have a wave generator on the left. Let's say call a wave, the forces on A, that is sending by Newton's third law a wave to the right. So look at a Newton's third law, action sending the wave generates a reaction. Now, when the wave hit the wall on the right side, then you have the wave is giving momentum to the wall. Let's say it gives 50% of the momentum, and then it bounces back to A. So you have now that the equation should read the forces on A minus forces on B, and then you have a net that would be toward the left side, because you have the force of the reaction minus the momentum spent on the wall, and then you have the Q factor of the cavity that is bouncing back and forth. And let's say 50% went to the right wall, and the other 50% spent, let's say, bouncing back and forth. Now, how do you explain that? Because by all reasoning, by standard physics, it should be a net zero. But when you look at Newton's third law from that viewpoint, the forces should be, there should be a net force toward the left and not toward the right.
Yeah, this, as I was saying earlier, this is kind of my concern, is that you're sending one way, a blue shifted wave to the right, and you're then artificially sending a red shifted wave to the left. Now, I'm not sure what happens to that, the energy and the momentum of those waves when they reach the other side. It's not clear to me if it's somehow being redirected or reused in this four-wave mixing process. I guess, I'm not an expert in this field. As I say, I'm really only presenting this because Larry Reed himself doesn't want to present it at APEC for his own, I don't know, for his own reasons. So I'm just hoping to kind of give this a wider audience. I think the idea is that that energy is redirected or reused in some way. It's not. I mean, as I say, he mentions here that he says that the light beam will undergo momentum reversal, so it cancels the momentum of the incident wave. But my concern is, what happens to the energy of each wave when it hits the other side? So that for me could be a limiting factor here, why it may not work. The idea, essentially, he wants to, he's ignoring or has otherwise compensated for what happens at the ends, and he's essentially generating a matter wave of the right shape that corresponds to an external force. He's saying that we can effectively create an internal force by mimicking the effect of an external force on the shape of this standing wave. So he's not concerned or has somehow already taken care of what happens at the ends. And he's saying, no, just all we're doing is modifying this wave in the middle. And that, in theory, as I say, if it is an inverse Doppler effect, if that is possible in this situation, then in theory it could create a thrust in one direction. But yeah, I think for me it's still an open question about what happens to the momentum of the two individual waves, because the idea is not that you bounce the same wave back and forth, but you generate one wave one way, another wave the other way, and they interfere or create a standing wave in between. And what happens to the wave at each wave at its destination, I don't know.
Well,
I'm assuming it's somehow involved in the phase conjugate mirror reflection.
Because I have done an experiment in that area, I know that a standing wave is not necessary. I mean, I stand by it, that it should be on the F8, it's kind of a different, the equation that you have there on the website. The net would be B minus A, and I say actually it's the other way around. But the standing wave does not play very much of a role. I mean, you have a role of destructive and constructive interference in there. But because I've done the experiment, and I know, and beauty is that I videotape my experiment, so I know it's going to be on the A side, which is the argument I have against the M drive Rogers Sawyer, that in some situation I think he has a backward. So has he taken into account the role of constructive and destructive interference on the wave in the cavity? What would happen there?
I think, as I say, I think his work is focused to create a moving standing wave of a certain shape, certain phase.
Solitone.
Yeah, I suppose, yeah. And he is associating that with the de Broglie matter wave. He's saying this is what's sometimes called the pilot wave, de Broglie-Bohm wave. It's either that or it's a macroscopic version of it. And he's saying that if we can create a moving standing wave, not a static standing wave, but a moving shaped wave, that it's the same shaped wave you would get if you pushed it externally. So I suppose if you had a single generator, inside the cavity, and then you pushed it artificially yourself from outside, you should see this matter wave forming. And he's then saying is that we can artificially generate that same shape of wave inside. And admittedly, it sounds like pulling yourself up by your bootstraps, but he's saying that if this represents an inverse Doppler effect that would allow it to shift itself, you're still supplying it with energy from external sources. So it's not propellantless. It's not, well, it's not a free energy system. It still requires energy, but it can somehow move itself. Yeah, and I agree. There are unresolved issues, I think, around what happens to each signal at each side, because he doesn't want to bounce it around. He's actually artificially just sending two waves and then absorbing them or redirecting them in some way at the ends. That's my understanding.
Thank you.
Anyway. Okay,
thank you.
thanks.
That's a good explanation to think about. Thank you.
Okay.
Awesome, Harold. Thank you. Let me see. Let me go back to Michael, sir.
So I'm just like thinking about this, and so for example, if you, it seems if you had a resonance state where you have two waves, say you have a 3 hertz on one side and then 9 hertz on the other side, you would get basically you get a resonance state there because you could fit basically 3 of the 9 hertz in 3 hertz. So you could get a resonance state there at 9 hertz, and that would occur on the side where the 9 hertz is. You get where I'm going with this? So
Yeah,
you could make one side energy, basically have an excess energy. The question is getting it to be inertial energy. So basically assuming that inertia and electromagnetism.
Yeah, I think because this is what he's saying is that by the degree of how far out of phase the two waves are, that is kind of in some way proportional to the amount of force you're pushing it with.
Right. Well,
So,
actually, you have to have constructive interference between the two, and so basically at the there would be constructive interference between the 3 hertz and the 9 hertz wave. But
yeah, I'm just thinking, I'm just going back to the notes because he did mention something about the difference between consonant states and dissonant states. That, you know, that this is, I forget the exact terminology, but I will just see what I can find. Because again, he obviously understands this a lot better than I do. So, yeah, so, right, okay, so moving standing waves within a cavity resonator in motion, they become contracted. The resonator mass motion represents a disequilibrium or dissonant state as one or both standing wave end nodal points are displaced from the end walls. So it's when you're trying to displace the nodal point away from the wall, that's where this the tendency then comes. It needs to correct itself, so it's trying to reestablish the node on the end wall. So I think that's.
I see.
So.
Okay. So it's a phase state, essentially. It's a phase.
Yeah, the thing you can manipulate the phase as well as the frequency.
Okay. Okay, thank you.
Okay. Yeah.
Awesome. Okay, sorry, let me put your hand down, Michael, and thank you, sir. So let me see, other questions for Rob Chambers? And again, you know what, let me read my thing here. So you can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. So again, Option Y or Alt Y. Yeah, and again, Rob, your drill down was just amazing.
Well, as I say, I'm trying to do him justice, but I also try to avoid too much complicated equations.
Well,
just
you
to
know,
kind of-
I've talked to Larry Reed. It's been a while, but we talked to him twice, and he said he didn't feel comfortable presenting in public. So thank you for sharing his work. You know, and I think he was pretty, at least with me, he was pretty open about, if I remember correctly, he'd said that he went through, basically, he just went through all the literature that he could find, and that was what he was able to pull together, you know?
Yeah.
So.
Yeah. Yeah, in fact, the presentation that I took a lot of that information from, it goes a lot further into gravity as well. He has some theories about gravity and how it relates to electromagnetism as well, which I don't claim to understand, so I left that out of the presentation. I wanted to try to keep it to things that I could get my head around. So yeah, if anyone looks at his work, there is a lot about gravity as well, which is above my pay grade at the moment. So
Yeah, no,
yeah.
I loved his book. I mean, it's incredibly detailed. He did tons of research, tons of synthesis. There's so much in there. Yeah, you know, and that's why I'm so excited that you're able to present it, because I mean, there was a lot. You know, I wish that he would come on, and who knows, at some point maybe he will. So
Yeah. So yeah, I mean, I'm happy to wrap it up now. If, as I say, because it's not really my work, I'm probably not the best person to ask, but I just tried to give it as much exposure as possible.
Okay, well, let me do this. Let me go back to Harold, and we do have Jarod with us, so we could go to Jarod early, or, you know, the other thing that we could do is, we've got about half an hour. Mark Sokol wanted to present for MUFON, and he was worried that the presentations were going to wrap up there. So let me go back to Harold really quick, though, and we'll.
One more question. I mean, actually, about two subjects. One of them, what are the thermal dissipation problem that happened there? You know, for example, the heat of the wave, how the energy is spent, and have you done any thinking about the electromagnetic property of the material of the cavity? What kind of interference that the material causes on the wave propagating inside the cavity? And have you considered metamaterial or something like that? What is the level of research that he has in those two areas right now?
Yeah, in terms of thermal management, I don't think there's anything in his theory about that. I think he's really looking at the fundamental principle rather than a practical implementation. So I don't think he's put a lot of thought into what happens to the heat that you generate. Obviously, you're going to generate a lot of heat with this thing. So, you know, yeah, I mean, potentially you could imagine there'd be if this metamaterial that he's using, that he's proposing to disperse, and effectively it looks like it's dispersing energy around the outside anyway. Of course, radiating things into space is not easy. So maybe this is more of an atmospheric vehicle than a space one, because in space, I know thermal dispersion is a big problem, just radiating out the heat. So yeah, no, I don't think he's really gone into great detail about the mechanics and the thermal management.
Has he done any experiment, or is 100% theoretical?
I don't know. I assume it's theoretical. I don't think he describes any experiments in his work.
Yeah,
So
that was the impression that I gotten with Larry, was that it was all kind of on paper.
Yeah. Essentially, the core principle here, as I see it, is that the first half of the presentation, or the Jennison's work, seems to be pretty standard in terms of classical physics. Even he's published several papers around this topic, and they're all peer-reviewed in major, respected journals. So presumably, in terms of physics, that's absolutely fine and not questioned. Although it's a simple model, it's probably too simple. But Larry Reed's work really depends on whether or not you can achieve the inverse effect, whether you can, as I say, if you're generating this matter wave, can you generate it internally. If you know what it looks like, you know what the waveform looks like, can you generate it yourself? And if you did that, would you then create thrust? So yeah, it does sound like the ultimate in, you know, pulling yourself up by your bootstraps, but he's saying that, well, we have all these other effects which have inverses, which exist. So for example, you can turn a generator into a motor and vice versa. We said the Einstein de Haas effect and the Barnett effect are opposites. So there is a tradition, there is a accepted set of effects in physics which have an inverse. So if this has an inverse, maybe we could use it. So I think that's his fundamental, his message.
If we use the inverse effect, how is the energy being radiated out of the cavity? I mean, what happens to the energy when the two waves cancel out? Does it become radiation, thermal energy, electromagnetic, alpha wave?
Yeah.
What is it? What happens?
Yeah, that's I don't think that's made clear. I mean, it may be in there somewhere, but I haven't found a clear kind of explanation. But yeah, I think there is definitely an issue with what happens to the energy, especially if it opposes the effect you're trying to achieve. So, you know, will it actually move, or will it just sit there and radiate heat or microwaves or X-rays or whatever, you know, from both ends? So I think there is a question, an unresolved question there. Yeah.
Awesome. Okay, so let's do this. So I want to, let me see, I'm going to put this thing back on gallery view. Everyone, again, at the end of our Q&A session, let's give a giant applause to Rob Chambers. Rob, you are the man. That was an awesome presentation. I cannot thank you enough. That was a lot to pull together. I mean, you blew my mind. So,
well, thank you. You're welcome.
Yeah. So let me do this. Let me see if I mean, we are ahead of time, and that's totally cool. Let me see if Mark is it
it's a little bit slow here. It's a little bit slow here at the conference right now because everyone's inside listening to a presentation. How about we wait a little bit until all the presenters are back out here?
Okay. So why don't I do this? Do you want me to go to Jarod then and see? Because we have Jarod with us, we can do his presentation and Q&A, and then.
I'd love to see Jarod's presentation. Go for it.
Awesome. Okay. Thanks, man. Okay. So Jarod, we do. Oops. Let me do this. I'm going to ask Jarod to unmute. Okay. Well, you know, actually, you know what, Jarod? But before you do that, let me stop your screen share. Let me do a brief introduction. Okay. Okay. Let here. I'm just going to stop your sharing. So, okay. Sorry about that. Yeah.